Hello everyone, I'm Sid from Carnegie Mellon University. This talk presents our work on Searchable Hidden Intermediates framework for building end-to-end models of decomposable sequence tasks. This work was done along with my collaborators Brian, Vikas, Florian, and Shinji. This talk is outlined in 6 main parts, where I will first discuss what is compositionality and its benefits towards building complex systems. I will then talk about our proposed Searchable Hidden Intermediates framework, followed by an instance of this framework applied to speech translation using our multi-decoder model. I will then present the benefits of our framework and support them with some additional generalizability tests. Finally, I will conclude with some key takeaways of our work. Okay, so let's start. Compositionality is the principle behind building complex systems by composing together simpler subsystems. For example, speech translation systems which seek to process speech in one language and output text in another language can be naturally decomposed into the transcription of source language through automatic speech recognition and translation into the target language through machine translation. Traditional sequence models exploited compositionality to build a pipeline of simpler subsystems to solve a complex sequence task. Such cascaded approaches have been widely used to build practical systems for a variety of sequence tasks like hybrid ASR systems, phrase-based empty systems, and cascaded ASR empty systems. There are many attractive properties of cascaded systems that are missing in end-to-end sequence models. In particular, we are interested in the strong search capabilities of the cascaded systems to compose the final task output from individual system predictions, the ability to incorporate external models to rescore each individual system, the ability to easily adapt individual components towards out-of-domain data, the ability to monitor performance of the individual systems towards the decomposed subtask. Now we will introduce the proposed Searchable Hidden Intermediates framework, where we will start by defining a decomposable sequence task. If there is an intermediate sequence B for which A to B sequence transduction followed by B to C prediction achieves the original task, then the original A to C task is decomposable. For instance, we can decompose speech translation or spoken language understanding using ASR intermediates and speech recognition using phoneme, character, or BPE intermediates. We present a general end-to-end framework to exploit the natural decompositions in sequence tasks, which seek to predict some output C from an input sequence A. We first decompose the sequence task with the sequence B as intermediates. Then, during training, a neural network subnet A to B maps A to a sequence of decoder hidden representations of the sequence B. Then a subsequent subnet B to C maps these hidden representations of B to the final probabilistic output space of C. Note that C can be another sequence or even a categorical class, like in some spoken language understanding tasks. During inference, we find the best approximation of the hidden intermediates using beam search and pass it to the subsequent subnet B to C. When the decoder from the subnet A to B is passed with ground truth previous tokens, the hidden intermediates are void of search errors. These oracle hidden intermediates are used during training and for monitoring performance of the subsequent subnetwork. Now we will apply our general framework in a sequence model we call the multi-decoder. The multi-decoder model shown here is a speech translation model consisting of two subnets, the ASR subnet and the subsequent empty subnet. The architecture is essentially two encoder-decoder models, one for each subnet. Notice, however, that the empty subnet encodes the hidden representations from the ASR decoder rather than some discrete representation of text. The hidden intermediate representations produced by the ASR decoder may engender errors from the ASR subnet. To avoid propagating these errors in the downstream empty subnet, we also propose a variant of the multi-decoder that includes a multi-source cross-attention in the ST decoder. Here, the ST decoder is conditioned on not only the ST encoder representations, but also on the ASR encoder. We call this ST model the multi-decoder with speech attention. We test our multi-decoder models on the Fisher-CallHome corpus, which is a speech translation dataset consisting of 170 hours of Spanish phone call recordings, along with their Spanish transcriptions and English translations. In these results, we compare our multi-decoder and multi-decoder with speech attention models to cascaded and encoder-decoder baselines. The multi-decoder model shows a 1.9 and 0.9 BLEU improvements over the cascaded baseline on the Fisher and CallHome test sets respectively. The multi-decoder model also shows 5.6 and 1.5 BLEU improvements over the encoder-decoder baselines. Further, the multi-decoder with speech attention extends these gains with an additional 1.5 and 1.3 BLEU improvements over the multi-decoder model without speech attention. In addition to these results on the Fisher-CallHome corpus, we conducted experiments to highlight various other benefits of our framework, which I will present in the following slides. One benefit of our framework is the ability to use external models to retrieve better hidden representations at the intermediate stages, such as ASR in the ST task. By using external models like language models or CTC models trained on the same Fisher-CallHome data, we found that we could improve the ASR hidden intermediates and ultimately improve the overall ST performance as well. And we found that this was true for both the multi-decoder with and without speech attention. Without speech attention, the multi-decoder improved by 1.1 BLEU and 0.8 BLEU through ASR rescoring with external models. Similarly, the multi-decoder with speech attention improved by 0.7 and 0.1 BLEU. Another benefit of our framework is the ability to monitor the performances of each individual subnet. For various complex tasks, this performance monitoring can tell us valuable information about which portions of the overall task are working better or worse. For example, we found that for the multi-decoder model that achieves 52.7 BLEU on the Fisher dev set achieves 22.6 word error rate on the ASR subtask and 64.9 BLEU on the MT subtask. With speech attention, the multi-decoder that achieves a higher 54.6 BLEU on the same dev set achieves 22.4 word error rate on the ASR subtask and a higher 66.6 BLEU on the MT subtask. We also conducted a study on the effect of beam size at the intermediate search. We found that better beam search for the ASR hidden intermediates does in fact lead to improved overall ST performance. This increase in the overall BLEU score can be attributed to the improved ASR subnet performance. In the figure, we show several different beam sizes on the x-axis. In the blue line, you can see that the ASR subnet improves with increasing beam. In red, you can see that the overall ST performance mirrors this trend. We also conducted a study on error propagation. While the multi-decoder without speech attention is susceptible to this problem, the multi-decoder with speech attention, we expect, is able to avoid a lot of this error propagation effect. To study this difference, we split our dev set into 3 buckets of utterances according to the multi-decoder's ASR subnet performance. We found that on the easiest bucket, the multi-decoder manages to outperform the encoder-decoder baseline. This is as expected since the error propagation effect here would be less severe. However, in the more difficult bucket of 40% to 80% word error rate, multi-decoder performs worse overall than the baseline encoder-decoder due to its susceptibility to error propagation. Speech attention fortunately can resolve this problem. We found that in the same bucket where the multi-decoder suffers from error propagation, the multi-decoder with speech attention is still outperforming the baseline encoder-decoder. For extremely difficult utterances in the greater than 80% bucket, ST performance for all 3 approaches is suppressed. Next, in our penultimate slide, we discuss the generalizability of our framework. Our framework has the ability to adapt individual components of our end-to-end model towards out-of-domain data. We show that rescoring the ASR subnet with an in-domain language model improves ASR with around 10 word error rate, improving the overall ST performance by around 2.4 BLEU. Compared to an in-domain ST baseline, our out-of-domain multi-decoder with in-domain ASR rescoring demonstrates the robustness of our approach. We also applied our framework to decompose the speech recognition task itself. The ASR task can be decomposed into various levels of decompositions with phoneme, character, or byte pair encoding based intermediates. With experiments on the ASR portion of Fisher-CallHome corpus, we found that the multi-decoder presents strong results on both the Fisher and CallHome test sets. Of these three intermediates we experimented with, BP intermediates performed the best overall. The multi-decoder with BP intermediates improved by 3.5 and 6.4 word error rate compared to the baseline encoder-decoder on Fisher and CallHome respectively. And finally, we extended our ST experiments to other language pairs from Metze corpus, specifically the English to German and English to French datasets. This experiment also tests whether our proposed techniques scales with the availability of larger amounts of training data. The Metze language pairs have around 500 hours of training data compared to the 170 hours of Fisher-CallHome. Again, we found that the multi-decoder with speech attention outperforms the baseline encoder-decoder. In our experiments, we showed a 2.7 and 3.5 BLEU improvements over the Metze encoder-decoder baselines on the English to German and English to French test sets respectively. Further, ASR rescoring gives an additional 0.1 and 0.4 BLEU improvement. Okay, now I would like to conclude with some key takeaways from this work. Our end-to-end framework exploits compositionality to learn searchable hidden representations at intermediate stages of the sequence model. There are various benefits of the searchable hidden intermediates framework. Our framework brings several strengths of cascaded systems into an end-to-end framework, including search capabilities, external model rescoring, domain adaptation, and subnet monitoring. Further, we can avoid error propagation unlike cascaded systems. When applied to speech translation, our framework improves over the previous state of the art by around 6 and 3 BLEU on the Fisher-CallHome test sets and 3 and 4 BLEU points on the Metze test sets. Thanks everyone for listening. Please reach out to us by email or come to our poster if you have any additional questions.